Hello everyone. My name is Suraj and the topic of my presentation is cathodoluminescence. Now let us discuss what exactly is the cathodoluminescence. So before going to the cathodoluminescence, let us first understand what exactly is the luminescence. So luminescence is basically the spontaneous emission of a light without thermal uh, thermal stimuli. So what exactly is causing this such spontaneous emission of light? That depend upon various factors, and accordingly it is named. For example, we all must have seen a flying firefly. So it glows, and why it glows? It glows because of phenomena called the bioluminescence. That is basically some biochemical reactions occurring in its body. And to be more specific, it is basically um an enzyme called the luciferase, which is responsible for the generation of bioluminescence in firefly. Similarly, such behavior is shown by most of the deep sea creatures where the light is not present. And similarly, it could be also seen in some microalgae and other microorganisms. Similarly, we have the phenomena of a fluorescence, wherein the material first absorbs the photons and later re-release them once the photon incidence ceases. And if it instantly emits the light, such phenomena is called fluorescence. If this phenomena is quite delayed, it is called the phosphorescence. And there could be a chemical reactions that could generate photons, that is called the chemiluminescence. And this phenomena may occur in certain crystals. For example, the quartz, upon some mechanical stress, when they're subjected to some mechanical stress, they also produce light, and this phenomenon is called the triboluminescence. And in some cases, when the material is subjected to ionizing radiations, for example, alpha particles or gamma rays, then they also can produce the luminescence, and that is called the radioluminescence. Now, once we know what is the luminescence, now let us understand what is cathodoluminescence. So here the extra term is the cathode, and we know cathode rays consist of electrons. So this is the luminescence generated because of incidence of the electron on the material surface. So when a beam of electrons is incident upon a material, then it generates light, and we'll understand what are the phenomena involved in that. So we can see here a beam of electrons is interacting with the material and is emitting a light. So this phenomenon is called the cathodoluminescence, and it was observed by Crookes in the 1879. At that time, the term electron was not coined. So he used cathode rays upon the calcium sulfide, and he found such a luminescence phenomenon. He called it cathodoluminescence because he used the cathode rays. And then uh, the light or the radiation, the electromagnetic radiations which is generated, composed of a range of spectra, that is right from the UV to the near infrared. So it covers a huge range of optical spectra, and that depends upon a lot of factors like what is the energy of the incidence electrons, and what are the transition energy gap between when the electron is interacting with the materials. And yeah, so let us now understand what are the different phenomena that do occur when a electron interact with the material. So there are a multitude of phenomena that occur. For example, we can see here there is a beam of electrons, and it is incident upon a material. So it could be backscattered, it could be scattered, and these are studied under the scanning electron microscopy. And the interaction of electron with the material may generate X-rays. So we have energy dispersive X-ray spectroscopy. And similarly, if the electron is energetic enough or the material is thin enough, then the electron may pass through the materials, and such electrons are called transmitted electrons. which gives a lot of information about the material properties, which are studies under the transmission electron microscopy. Then we have a scanning transmission electron microscopy and the electron energy loss spectroscopy. And out of all so many phenomena, one phenomena that occurs is the cathodoluminescence. Okay, wherein a photon is generated when an electron is interacting with the material. Okay, now let us understand what are the different types of the cathodoluminescence. So there are basically two types of cathodoluminescence. It could be coherent or it could be incoherent. So in the incoherent, the uh, light which is generated is not in phase relation with the excitations, and it is basically an unpolarized light generated in case of the incoherent. Herein, the electron is excited from the valence band, it go to the conduction band, and then again, it when it return back to the valence band, it releases light. It releases a photon, whose energy is equal to the energy gap between the conduction band and the valence band. And similarly, coherent, uh, in case of the coherent seal or the cathodoluminescence, the light which is generated is polarized, and the light is which is generated is in well-defined phase relationship with the emitted photons. And these two phenomena, that is incoherent and the coherent, they occur simultaneously, but the necessary condition for the occurrence of the CL emission is that there should be a difference of the refractive index with the vacuum, which is usually the case. So the coherent emission do occur always, but its probability is quite low. It is just 10 to the power minus 4 photons per incoming electrons, and therefore it is very less pronounced as compared to the incoherent cathodoluminescence. Now, why CL? What is the need of a cathodoluminescence? So, cathodoluminescence has been used for a long time in geological sciences for the characterization of minerals. But nowadays, since the last 15 years, this has again become a very interesting topic for the research, and it is because of the reason because of the uh, electron has a such a small wavelength that it could be used to study the features at the nanoscales, because here we can see uh, the wavelength of electrons at 5 kilo at the energy of 5 kilo electron volt is 0.2479 nanometers, which in case of the SEM, in the case of transmission electron microscopy, which is where the usually high energy electrons are used, you get to see a more the wavelength is more and more lesser, and therefore you can study the more intricate and the more minute characteristics of the materials you're interested in, and therefore uh, the phenomena uh, uh, like the plasmon confinement, the band gap variation, the structural defects which occur at a nanoscale level could be easily studied with the cathodoluminescence, and therefore cathodoluminescence has become a subject of interest nowadays. Okay, now uh, let us understand what is the setup of the instrumentation in the cathodoluminescence. So we don't have any different instrument for the cathodoluminescence. So this is basically could be done in an SEM instrument. We just need a detector. So this is a scanning electron microscope, and you can see here the electron gun, which usually shorter as compared to that we see in the transmission electron microscope. And what could be the reason? The reason is just because in a scanning electron microscope we need a electron of a lower energy, so we do not need a longer electron gun in order to accelerate it to higher energy, and therefore this much is enough, because in the SEM, that is Scanning electron microscopy is basically used to study the surface phenomena. We do not need a high energy electrons which can penetrate and transmit through it. So we need a lower energy electrons, and therefore the electron gun is shorter. So what is exactly the setup for the cathodoluminescence detection? So we have usually a parabolic mirror just above the sample. So the electrons come through this. There is a small opening here in the parabolic mirror, which allows to pass through the electrons and interact with the samples. And upon interacting with the samples, the photons which are generated, they are reflected by this parabolic mirror and directed towards the imaging camera, and which detects it. Now, what are the sample preparation steps that are involved for the cathodoluminescence? So it is more or less similar to the sample preparation that we do in case of the STEM, because the same instrument we are using. So what exactly we do is that we take the sample, we mount it on the holder, and if the sample is non-conducting, then we are required to make it conducting by coating it with the gold or the carbon tape. So, and also if we use the powder sample, then also we use the carbon tape in order to fix the sample at one place. And we need to ensure that the sample is vacuum compatible, because we know that we maintain a very high vacuum in this, and this is because if there would not be vacuum, then the electron beam would interact with the particles of the air, and that would create errors in our measurements. Now, and then we need to do some configurations for the instrument that may involve the adjusting electron beam energy, beam current, and imaging parameters to optimize the CL signal detections. Then we need to carefully insert the sample holder into the SEM chamber and do the proper alignment. And thereafter, we'll take the intensity measurements, spectral analysis, uh, whatever the parameters we are interested in. Okay, now let us understand with the help of an example about the application of a CL. So this is an example wherein we are intending to find uh, the dopant. So we have two samples of aluminum nitride. One is doped with the europium and another is not doped with the europium. So our intention is first to find which of the sample is doped with the europium, and second is what is the distribution of the doped material inside the substrates. So from the first graph, which we can see here, which is the normalized CL spectra of the undoped and the doped materials, we can find that at nearly 360 nanometers, both the materials show a peak, which is basically due to the presence of some defects in the parent materials. But at the 550 nanometer, we see a peak only in one case, and this corresponds to the doping of the europium, that is 0.2% doping of the europium. And similarly, now we know that in which material the doping has been done. Now let us see what is the distribution of the doped material inside the substrate. So we can see here, this is the EDS spectra, and we can see that at the boundary we have the europium, and in the grains we have the aluminium nitride. Similarly, these findings were confirmed with the help of CL images at 360 nanometer and 550 nanometers. We can see the distribution of the europium around the grain boundaries, and similar is in the case of SEM. We have here the presence of the doped materials, and similarly in the case of the EDS mapping, we can see the distribution of a europium around the grain boundary. Next is, what are the application of CL? So cathodoluminescence has a wide applications in the different fields. For example, in the geological analysis, we have minerals, we use it for the detection of minerals and the different and its compositions. Similarly, in the case of photonics and plasmonics, we use the nanophotonic structures in the metamaterials study. In material sciences, we use it for the phosphor, ceramic, and the polymers characterizations. In semiconductor characterization, we use it for the band gap detection, the defects, and finding the dopant distributions, as we see in the previous examples, the distribution of europium in the uh, aluminum nitride sample. Now let us compare the CL with other SEM techniques. So we have the EDS, that is uh, energy dispersive spectroscopy, which is used for the elemental composition and the phase identification. Similarly, we have electron backscatter diffractions, which is used for the crystallographic orientations and the crystal structure and the defect measurements. Similarly, we have scattered electron detections, which is used for the surface topography, as we normally do in the SEM. We have a backscattered detection, so which is used for the material contrast, composition analysis, and the elemental mapping. So, and when we see at the cathodoluminescence, so this include a whole range of parameters that we can measure. So it has we can get a huge range of transition from 0.5 to 6 electron volt. We can use it to measure the compositions, the crystal structure, the band gap, the dopants, the crystal defects, optical resonance, refractive index, and all. Now, what are the advantages of CL imaging? So CL imaging provide a high resolution. Why? Because electrons have a very small wavelength. The smaller the wavelength, higher the spatial resolution you get. And it involves a broad spectral information from UV to the infrared. And we can use the CL imaging and combine with the other imaging techniques. So it provides a complementary information about the materials, morphology, structures, compositions. And it could be used for the depth resolved studies. Electron penetration depth is tunable because if we increase the energy of the electrons, so it can be deeper. And it is the type of progress in the contactless inspection technique. So that is another advantage of steel. And these are the references that I have used. And thank you so much.